Hey, chemistry crew, Mr. Collier here. I want to go over pages 22 and 23 in your gases packet, where we are continuing to work with the ideal gas law, which looks at a snapshot of a particular gas, looking at its pressure, volume, how many moles of the gas you have, and its temperature. So we're always using this equation, PV equals nRT. However, as I mentioned yesterday, I like to rearrange for the variable that they're asking me to solve for. So I usually read the question, kind of highlight the numbers and think about what they are, right? What is the volume? So I'm solving the equation for volume, and then I'm leaving everything else where it would go. If it contains 3.2 moles, so there's my number of moles, temperature of 20 degrees Celsius, so I need to convert that into Kelvin. I'm going to use my gas constant, 0.0821, and standard pressure is 1 atmosphere. Plug in the numbers, get your answer. Remember, all the answers are at the bottom if you just want to see the correct answer. Number 5 I love because it says calculate the volume which 1 mole of gas would occupy at standard temperature and pressure. So I rearrange the equation again for volume. The number of moles is 1, 0.0821 is my gas constant. Standard temperature is 0 Celsius, which is 273 Kelvin, and standard pressure is 1 atmosphere. And when you multiply these numbers, you get a number that looks very familiar, 22.4. This is that whole Avogadro's law. Any gas takes up 22.4 liters at standard temperature and pressure. So there's the kind of math from the ideal gas law that backs that up. Question 6 here, we're getting into some of the slightly trickier ones. It says what volume, so I'm solving for volume, would 20 grams of CO2 occupy at a temperature of 25, so convert that to Kelvin, and a pressure of 105 kilopascals, so I have to convert that to atmospheres. That's this guy right here. And I have my gas constant, but where did this 0.455 moles come from? So let's go back over here. It didn't tell me moles, it told me grams. So I need to convert from grams to moles. So I take carbon dioxide and I divide the 20 grams by the molar mass of carbon dioxide to get the number of moles of carbon dioxide. So that's where that number came from. Now I can solve it. And that's what makes this one a little bit trickier. They gave you grams, not moles. You needed to do a conversion before plugging them into the equation. Number 7 has a similarly tricky question. It's got a 23.6 gram sample of an unknown gas. Okay, so at first it seems like, well, if it's an unknown gas, how am I going to figure out moles? But we'll get there. It occupies a volume of 12 liters at standard temperature and pressure. So here's a good thing about this. We actually know everything but the number of moles, so I can actually solve for moles. I know the pressure because it's standard pressure, so that's 1 atmosphere. I know it's 12 liters. I know the gas constant always, and I know the pressure is 273 because it says standard temperature. So now that's going to spit out the number of moles that I have of this gas. And now, and this is rare, we've not really done too many problems like this, it's actually the molar mass is what I don't know, but I know it's 0.536 moles, and I know that it's 23.6 grams. So what's the molar mass? So when I solve here for X, I'm going to get that it's 44 grams per mole. Interestingly enough, that actually doesn't tell me exactly what gas it is, because there's actually a couple gases that have 44.0 grams per mole. For example, N2O in our next problem, but also carbon dioxide. So number 8 here, what is the mass of nitrous oxide, N2O? So I'm looking for mass, which means I'm going to have to solve for the number of moles because I can relate moles to mass. I've got the volume, 20 liters. I've got the pressure in kilopascals, but I need to convert that to atmospheres. Didn't actually show my work there, but I did convert it to atmospheres. And I've got my temperature, which I convert to Kelvin, and as always, the gas constant. That's going to solve for the number of moles. I'm going to multiply by the molar mass of this particular chemical, and I'm going to get the number of grams. We can also solve for pressure, like here in number 9, what pressure would be required to contain 100 grams of something. So when I have 100 grams, I'm going to need to convert that to moles. So I divide by the molar mass of this particular chemical, which I get from looking at the periodic table. I get the number of moles of that chemical, and I put that into the N of the equation. I've got my gas constant, I've got my temperature converted to Kelvin, and I've got my liters. All of that allows me to calculate the atmospheres. All right, so that's page 22. You also did page 23, so let's take a look there. And I think I might not do all of these. Again, here we're solving for pressure. We're given moles, temperature, volume, very straightforward. Here we're solving for volume, and we are given the pressure, the moles, and the temperature in Celsius, which is just a single conversion. In number 12, we have to do a gram to mole conversion, and then we're given a volume and a pressure, and so we're looking for temperature. Solve for temperature instead. Number 13, we're looking for grams, which means we have to solve for the number of moles. We're given the pressure, but need to convert it to atmospheres. We're given the volume in milliliters, need to convert it to liters. We're given the temperature, but need to convert it to Kelvin. That's going to spit out a mole number, and then we multiply it by the molar mass of oxygen gas. That's where that 32 grams came from. Oxygen is O2, and we get the number of grams. All right, 14 is one last one I want to go over, and it is a little bit tricky. We're looking at a pressure of very small, and we want to know the volume in milliliters of a certain number of molecules of gas at standard temperature and pressure. So first, I'm going to take the number of molecules and convert it to moles. We haven't done this in a while, but if I know how many molecules I have, I can convert it to moles by dividing by the number of particles in a mole, right? So a mole is 6.02 times 10 to the 23rd. This was only times 10 to the 6th, so that's much less than a mole. So that's why I get this tiny little number, less than a mole. I also can convert that very tiny pressure into atmospheres, and it's a very, very small, right? And so I take my very small amount of gas, my very small amount of pressure, plug them into the equation at standard temperature, and it's going to spit out a number in liters, which I did not show that here, and then you're going to slide the decimal to convert it to milliliters. All right, and that's it for that. Let me know if you have any questions on 22 or 23.